Today I'll be sharing with you some of the more special applications that we can do on ICPMS. Okay, so this is the agenda. I will give a quick introduction to what ICPMS, maybe a very short one because I'm sure there's a lot of experts here on the floor. I will run through three type of applications that we do on our ICPMS. Firstly, how we can automate the method so that it makes it easier for users to run the ICPMS. We'll look at using ICPMS or elemental analysis to identify geographical origins of food, where certain foods may come from. Okay, and lastly, I'll talk a bit on how we can analyze radioisotopes on ICPMS. Okay, so let me run through this quickly. So I'm sure a lot of you are familiar with ICPMS technique. So basically, it's an inorganic elemental analysis technique where we can measure most of the elements. Consists of two basic parts: the ICP, or inductively coupled plasma. So the plasma is a high energy source where we ionize the elements, okay, decomposes them, and then subsequently we try to measure the ions that's generated. Okay, the second part of the instrument will be the mass spec. Okay, so the mass spec, basically we use on most routine ICPMS analysis, we'll use a quadrupole. Okay, and the quadrupole can scan typically from in my slides I put 7, but typically you can scan from mass 2 up to 260 atomic mass units. Okay, so we can analyze the elements. We can gather isotopic information on the elements. Okay, and typically on the ICPMS we can measure from a PPT up to a ppm level. Okay, so in terms of food analysis, I would think that ICPMS is considered the gold standard for elemental analysis. Because it's very specific and it's very, very sensitive. Okay, so these are just to give you a brief idea on what we can measure on the ICPMS and some of the detection limits that we can achieve for some particular elements. Okay. Generally, it's widely recognized in the market right now. There's generally two types of ICPMS. Okay, so on the left side of the slide, you can see we have something called the single quad ICPMS, or now commonly in some papers they are referred to as ICPQMS. Okay, single quadruple MS. Okay, so I don't speak for other vendors. Okay, a disclaimer here. I'm only speaking for Agilent. At Agilent, we believe the best way to operate a single quad is using helium as a cell gas, okay, because it's a much easier remove polyatomics much more effectively. Okay, we do use a reactive gas on our single quad ICPMS, but we feel that there is some limitation. Okay, so basically for single quad ICPMS, like its name suggests, it only have one quadrupole, and the quadrupole is located after the cell. Okay, so there's there's no mass selection before the cell, and I will explain it in the later part of my presentation. Okay, but generally when we use a reaction gas in a single quad, the reaction chemistry may vary. Okay, so at Agilent we prefer to stick with helium gas as a simpler kind of cell gas. Okay, so on the right of the screen is what we call a triple quad ICPMS. Okay, or ICP-QQQ. Okay. I'm very proud to say Agilent was the first vendor, okay, to manufacture a triple quad in 2012. Okay, so this year is actually the 10th year of our triple quad, and we are at our second generation of triple quad ICPMS. Okay, and how we operate our triple quad, typically we will operate it with a reaction gas. Okay, so the importance of triple quad is not just the number of quadrupoles. Okay, so some vendors say they have 3 quadrupoles, some vendors say they have 4 quadrupoles. Maybe in future they'll say there's 5 or 6 quadrupoles. Okay, it's not important. But the importance of ICP triple quad is the ability to operate in a MS mode, or in chemistry term, tandem and MS mode. Okay, so that is the critical part of a triple quad. Okay, so we have two quadrupoles, and we have a gas cell in between the 2 quadrupoles. Okay, so with the quadrupole we can filter certain masses. Okay. And with that, we can use a reaction gas more effectively. So again, in my later part of the presentation, maybe I'll explain a bit more on that. Okay, so what are the challenges of ICPMS? Okay, so this is a very wordy slides. Okay, but generally it's agreed that ICPMS technique is a very fast and multi-elemental technique that a lot of labs would like to adopt, okay, for use for elemental analysis. Okay, but of course, adoption of these high-end techniques can lead to some problems. Okay, so there's a lot of feedbacks to say that ICPMS is a very difficult technique. It's hard to use. Okay. You need experienced users to operate the instrument. It's expensive, etc., etc. Okay, so it goes then this segues to my first application topic. Okay, so if you are interested in the application, okay, feel free to Google the reference number. Okay, in the slide. Okay, so it will let you have a look at the full the application note. Okay, so this is basically a way which we automated the method setup on ICPMS. Okay, so basically what this application notes describe is how we have something in the software that allows inexperienced user to just easily build up a method on ICPMS and start analyzing on the ICPMS immediately. Okay, so basically the user just have to follow the workflow that is set up in the software. Okay, so the key will be to highlight what's the analyze elements that you want to operate. There are some solutions that have to be prepared. Okay, so some tuning solution, some reference solution. Okay, that is required. Okay, so in my later slide, I'll show you some of the screenshots through the method wizard. Okay. Lastly, the user is actually just required to choose either do they want a faster type of analysis or do they want a lower type of detection limit for analysis. Okay, so once all this information has been entered into the software, basically the software will build up a method, and then the user can run this method that's built up. Okay, so these are some of the screenshots that's from the software. So basically, it's what we call a method wizard. Users typically just follow what is suggested in the wizard and go along with it. Okay, so you can see in the first slide, it will check what is the configuration of the instrument. Okay. Next is do you want to have some automatic building of the method, or do you want a more manual type? Okay, if the user is more experienced. Okay, selecting the elements. Okay. Setting up the different standards. Okay, so standards the users still have to prepare themselves. Okay, so some blank solutions. Okay, this is to let the software identify how much time does the sample required to be uptake before it can be analyzed, and then how much time is required to rinse out. Okay, so all this can be set up, okay, if there's an auto sampler. And lastly, as I mentioned, the user can decide between either you want a very high speed of analysis or you want a better type of detection limit type of analysis. Okay, and automatically the method will be built up into the software. Okay, and subsequently, if the user would like to run this method again, they can save the method. They can create another file from this method that is set up. Okay, so the proof whether this works or not is to run some actual samples. Okay, so in these application notes, it will describe. Okay, so some of the what we have done to validate this method set up on the software. Okay, so basically three certified reference material were prepared. Okay, and they were analyzed with the method that is set up. Okay, and I think there was some spike recovery done as well in the application note. Okay, I'll show you in the later slides. Okay, so these are the certified reference materials. Okay, you can see the certified concentration versus the measured concentration. Okay, and obviously they correlate quite well. Okay, and some spike recoveries done on the samples that were digested. Okay, so quite quickly, that is a method automation on ICPMS. So the takeaway here is ICPMS is not that difficult. Okay, if you have this type of software tools to help you. Okay. Next, we will look at how we can use elemental analysis to determine geographical origin of food. Okay, that means where certain food may come from which country, for example. Okay, why are you people interested in knowing where food come from? Okay, because it can tell a lot of information. Okay, it can tell whether it can be food from certain countries can be of higher quality. Okay, users nowadays want to know where is the location of the food they are eating. Okay, so where this is the label that is on the food, is it correct? Okay, and of course it links to everything links to food safety. Okay, consumers want to eat food that is safe. Okay, and certain places may have a better reputation than others. Okay. And the next point is there's an increasing focus on this ESG nowadays. So I think sustainability is a keyword that we hear again and again. Users or consumers want food that is produced sustainably. Okay, and all these right links back to how much a user pays. Okay, and how much a producer can earn. Okay. From the food they produce, and how much and how much a user will pay to consume food from certain locations. So it links back to a lot of all these fairness. Okay, do we pay our producers fairly? Okay, and are consumers being cheated? Okay, because the food is not labeled correctly and they are overpaying for certain food. Okay, so these are important in terms of the fairness. Okay, and obviously we hear a lot of all these. Deceptive labeling, okay, food coming from certain locations which is not true, or food adulteration, etc., etc. Okay, so we want to have a robust method in which we can do all these determination. Okay, and generally for to determine food origins with elements, I break them down into two types. Okay, so number one, we can look at stable isotope ratios. Okay, so we can look at some of the lighter isotopes. So lighter isotopes like hydrogen, carbon, nitrogen, oxygen. Okay, these are associated with the climate in certain areas. Okay, so the isotope may varies. Okay, according to different geographical places. Okay. We can also look at heavier isotopes like strontium isotopes to identify where food is coming from. Okay, but in in the examples I'm showing, we are not really interested in looking at isotope ratio, because isotope ratio will be a more kind of advanced technique for ICPMS. Okay, so we are interested in looking at just using inorganic elemental composition. Okay, either trace or macro elements. Okay, to determine where certain foods can come from. Okay. We can also use rare earth elements. Okay, that there are studies where certain farmers are using fertilizers enriched with rare earths, which it has been shown that it produce the plant can grow faster, the crops can grow faster. Okay, but I think for this presentation, I'm more interested in the macro and trace elements to doing food origins. Okay, so the previous presenters have talked about how all these elements can be absorbed onto plants. Okay, so earlier the presentation about arsenic. Okay, so we know that elements can be absorbed into plants. Okay, depending on the climate at that point of time, depending on the irrigation, depending on the type of soil. Okay, and all these elemental compositions can bioaccumulate in different part of the plants. Again, depending on the type of plants. Okay, and then so logically we should be able to use these trace and macro elements. Okay, as a fingerprint to identify where certain plants may come from. Okay, through studying the distribution of the trace and macro elements. Okay, so we will do a technique called elemental profiling. Okay, so elemental profiling, basically you have your food. Okay, you analyze the elemental content. The elemental content can be analyzed either on an ICP OES or on an ICPMS. Okay, and through the data that is collected, okay, we can do some statistical studies. Okay, so Agilent provides the whole solutions for this. Okay, we do have a software we call Mass Hunter MPP. Okay, Mass Profiler Professional. Okay, so basically it is a software that we use a lot on our LCMS to do proteomic studies, metabolic studies, but we find that it can be used to look at elemental profiling as well. Okay, so let me give you some examples and some applications. Okay, wine authentication. Okay, so wine authentication is wine is a big business. Okay, so you can see in this news article, it says that a lot of wines that is being drank in China is basically not labeled correctly. They are not labeled as where they come from. Okay, so this is a big issue regarding food fraud. Okay, let's look at this example. So this example will look at the impact, okay, of both the vineyard, okay, as well as the winery in and using elemental profiling to see if we can determine where the wine come from. Okay, so in this application, we are looking at about 65 wine samples from I think 5 different vineyards in California. You do have to screen through a large number of elements, okay, in order to determine which elements are statistically significant. Okay, so in this, like I mentioned, in this application, we not only look at the vineyards, but we also look at the wineries. So the wineries are where the wines are processed, and does that affect the elemental profiling as well? Okay, so this is the map from where the grapes and the wine were sourced. Okay, so 65 samples. sourced from 5 different locations, and then into 5 different wineries. Okay. To analyze the samples were basically diluted in 1:3 in 5% nitric acid to decrease the ethanol level in the wine. Okay, and then they were all measured. The data can be exported, okay, directly into the MPP software, where you can run different statistical profiling. Okay, so out of these 63 elements, only about 17 elements were determined to be statistically different. Okay, and if you can look at the chart, okay, that is drawn from this plot, right? You can actually see that, okay, the numbers are the vineyards. Okay, the alphabets are the wineries. Okay, so generally you do see a trend. Okay, that those vineyards that are the grapes that are the same. Okay, they are clustered more closely to each other. Okay, but in this study you also find that during the processing, okay, the wineries can contribute to some elemental content, okay, and then this may affect the identification of the wine as well. Okay. The next application is talking about rice. Okay, so the previous presenter have talked a bit about rice. Okay, so basically we are doing a similar thing. Okay, so this application was done by my colleagues in China. So we are trying to study whether we can identify where certain rice come from, which part of China. Okay, so we are doing the same thing. The rice were digested, the data were thrown into MPP and processed. We are doing a statistical study called principal component analysis. Okay. Okay, and in principal component analysis, you can plot it out in a 3D chart. Okay, and the 3D chart will give a good idea of where the different locations of all these rice. Okay, in this application, it did additional step. So in the MPP software, we can do a predictor class prediction model. Okay, so we can create a model, and then we can apply unknown samples to the model, okay, to check whether it will be able to predict the correct location of the unknown sample. Okay, and you can see in this example, out of the 24 unknown samples, in inverted commas, okay, the model was able to predict correctly 23 out of the 24 samples. Okay. Lastly, let me run through this quickly. Is looking at radioactive isotopes in ICPMS. Okay, so important date for our Japanese colleague. Okay, so March 11, 2021 was where the great earthquake happened. Okay, and there was a nuclear disaster on the Fukushima nuclear plant. Okay, so it spread a lot of contamination, radioactive contamination throughout Japan. Okay, and there was a lot of interest then to identify certain radioactive isotopes. Why these isotopes? Is because these isotopes are relatively long-lived radioisotopes, and they are usually indicative of a nuclear, a man-made nuclear, either nuclear testing or nuclear contamination. Okay, so there was a lot of interest to identify where all these radioisotopes are. Okay, and for radioisotope analysis, it's difficult to run on a single quad ICPMS. Okay, because all these radioisotopes they have isobars.
1 minute left.
Okay.
Yeah.
So basically, MSMS, okay, or triple quad would be a better type of instrument to run this type of analysis. Okay. Okay. So let me show you some examples. Okay. So to measure strontium 90, you can see on the chart here. So strontium 90, right, is strongly interfered by isobar zirconium 90. Okay. So to remove strontium 90, we do have to use some kind of a reaction gas to react away zirconium. Okay, and how we know that any reaction occurs is by looking at the enthalpy of reaction. So we can see strontium enthalpy of reaction with oxygen is positive, so that typically there's no reaction, and then zirconium there is a reaction. So we can remove zirconium by setting the different selection on the quadrupole. Okay, maybe I'll just end with this slide. Okay, so to show that whether this really works or not work, okay, basically we run a 5 ppm of zirconium standard. So you can see strong zirconium interference when it's in a no gas mode. That means without any reaction gases. And when we run with oxygen and H2 as reaction gases, you can see a clean spectrum at the mass 90. Okay, and it's estimated that the zirconium detection limit is about 0.2 ppt in this case. Okay, and there are additional examples which I will not go through. Okay, so similar examples looking at different radioisotopes using triple quad technology. Yep.
Okay.
Okay. Thank you.